Okay, so this is another problem from the physics teacher. I kind of liked it, so I thought I'd do this one also. Touch by an angle. Terrible name. It references a TV series from the 90s. Another interesting problem from the physics teacher. I kind of liked it. And it does it two different ways. I modified their conservation of energy approach to look at the approach we use in the course. So the system is kind of complex looking, consists of light, read massless, so I usually say massless, horizontal rod of length L, supported by two light, so these two light rods of length L. So right here, one rod, and over here, another rod. So points A, B, C, and D are frictionless pivots. And a small mass, or sphere of mass m, is attached to the horizontal rod at a distance d from the midpoint. What is the period of small oscillations of the system in the plane of the page? So it's been sort of displaced from the center. It's not a rigid body problem, despite the fact that it has rigid body linkages. It's not a rigid body problem because what's happened is that the body has been displaced, the rigid links are massless. So if we look at the entire body, first of all, we have a couple different forces that are going to play a role. So link B, C, which is the link in between, and this link, or this mass here, which has been displaced D, I've just got to put all these forces in. So I've got force 1, force 2, which is going to be acting at an angle theta. I have mg, and I have the total length of this thing. So sum of forces in y, F1 cos theta, F2 cos theta, minus mg, because the weight's going to be acting in there. And then I'll have opposing forces there in the x direction, and that will equal mx double dot. So that x direction is where I expect to see all of the displacement of this thing. Now, as a typical case that I do in the lecture, and one which you're probably really familiar with, is these are small displacements. We started with that as sort of the course or problem description, and we know from that that cos theta is going to equal 1. It's close to 0. Theta is close to 0, and sine theta is equal to theta. So we don't set it to 0, but we set it to theta, and it's x over L. L being the lengths of the support rods, not the length BC. So from that we get F1 plus F2 equals mg minus F1 plus F2 x over L equals mx double dot. So we got all the terms there and everything we need. So if we take the sum of moments, well, F1 is going to be causing a clockwise moment. F2 will be causing a counterclockwise moment, so that's negative positive, and the weight is also will cause a moment minus mg, and that will all equal to 0. So the entire system then goes F2 minus F1, and it's minus 2 mg over L. Okay, so that's all sort of works out really well. Mass of the rod. Okay, so everything's there. And just a reminder, this is still a particle, and if it's a particle, its size is 0. So it doesn't have any real moment. So force 1 mg over 2 and force 2 mg over 2, 1 plus 2d over L, 1 minus 2d over L. Both of those are going to depend on distances, and I end up with x double dot plus twice gd over L, script L over L times x is equal to 0. That's my omega squared. That's my period of vibration, and I end up with 2 pi square root L over L, LL over 2GD. Okay. We can do the same thing, and we can expand out. We're going to cheat a little bit, and we're going to redefine cos theta as 1 minus theta squared over 2. So y is approximately equal to L minus L cos theta. Oops, and there you go. And I just want to know what this distance is that it's displaced upward. And so L minus L cos theta, L over L theta squared over 2. So I got that. I've got this displacement. T is kinetic energy, 1/2 mx dot squared plus y dot squared. And y dot in this is going to assume to 0. X is going to equal L, approximately L theta, and x dot then is L theta dot. So T is equal to 1/2 m L squared theta dot squared. Y is approximately equal to d sine alpha. And so based on that, I can say, well, U equals the displacement, the vertical displacement of this thing. And so that's mgy, mgd sine L over L theta squared over L, mgy, mgd L theta squared over L, because I'm just going to substitute in that relationship for sine. So out of this, I get T plus U is equal to a constant. I end up with taking the time derivative. I end up with all these expressions, and I can get rid of these right here. And I end up at the end with this expression, ml squared theta double dot plus twice mgd L over L theta equals 0. And hey, look at this. It's exactly the same as what I got in the previous part. And that's my omega squared. So T is the same value, which is not a surprise. But what out of this, all I want to sort of point out is you can solve them a number of different ways. Generally, I would use a force balance. And you use the approach taken in the course and the lectures, but make sure in the end that you know your vibrations definitions. Thank you, and we'll talk.